control approaches for an intersection. Then we talk about the research gap. Then we go down to the research objectives, the research contributions, and then the proposed approach in this work. Then we look at our simulations and results, and then the conclusion to future evaluation. Because of the need for man to survive, man has always sought for ways to go from one point to another in such that it is beneficial. So we can say that mobility is as old as mankind, and we have seen over time that man has invented different modes of transportation. And when we look at the graph up there in figure 1, we can see that most people in Canada tend to rely on vehicular transportation. And to buttress that, we also see that according to this vehicular registration data from Canada Statistics, you can see that it is ranging between 1.5 million to over 2 million vehicular registrations every year. Now, what does that tell us? It tells us simply that there are a lot of vehicles that seek infrastructure to utilize. Now, the ideal way to handle this volume of vehicles is to create a pathway between every point of interest. That means if for us here, if for all of our houses, we have a path that links from one point to another in the form of a fully connected graph. However, it is not feasible because of cost, and so if it is not feasible, we have to minimize cost, and therefore we have to create road infrastructures that will create intersections. Now, if we create intersections of this form, automatically we will have vehicles merging at the intersection and then dispatching to the various points or destinations that they are requested. Now, intersections come in different forms and designs. They have varying capacities, and like I said, vehicles will come to the intersection and then take their routes to their destinations, and that would mean that they have to find a way to negotiate the intersection. So vehicles have to have a way to plan and utilize the intersection such that it is safe, and then to minimize delay and all of those challenges associated with an intersection. Now, if vehicles converge at a point and they have to plan and navigate an intersection, then delay is inevitable. Why? Because usually, following that we have high volume of vehicles, this will not be able to, the intersection capacity will not allow for each vehicle to pass at a time. And so that will bring about traffic congestion, and traffic congestion will result in traffic delays. Now, what will be the implication of traffic delays? At times you will have impatient motorists trying to drive through the intersection even when they are just get their time to pass, and so that could lead to traffic accidents. Now you also have when vehicles are waiting at an intersection, their engines are running, and so you have emissions of greenhouse gases, which has health implications. Also, you have the situations related to energy wastage because the engine is running, energy is being burned, and then also you have loss of economic time. And here, if we look at this graph, the table over there, you can see that in Toronto only in the year 2022, an average of 98 hours was lost for motorists within the Toronto houses. Now, so that is to say that a lot of time is being wasted due to traffic delays. Now, another challenge is when you have emergency vehicles going to provide emergency responses, there are traffic delays, then such victims of emergency situation are greatly affected. Now, we have an intersection. How then do we manage this situation for vehicles to safely navigate and minimize delay at such intersection? Now, different approaches are proposed, and one of them is the centralized approach. Now, this would include the static controllers, which assign static phase equations to the various flows. Then also we can have nice or dynamic approaches that control the intersection. Essentially, here we have a traffic light system and what have you that schedule the intersection. Different approach techniques have been used, such as the model predictive control, the mixed integer linear or non-linear programming, and then we have the genetic algorithm and what have you. Essentially, you will find that Webster's algorithm is what is often used in most intersection, which is usually the static control. Now, the challenge with this is that it is a single point of failure, because when the traffic control fails, model will be optimal. And then such models will tend to have high computational complexity. Now, another challenge is the fact that when you deal with traffic flows, you have a high level of uncertainty that is associated with that, and most of those approaches fail to take into account this uncertainty. Now, an approach that is able to deal with this as uncertainty as such is a tool called fuzzy logic. Now, which is what we are also using in this research, because it has the ability to handle this uncertainty very much. Now, we also have limitations associated with technologies. What you will find in today's implementations mostly is that we rely on sensors such as the inductive loops, pneumatic tubes, and then cameras. Now, you will find that such have limitations in terms of ranges. That is a detection range, which means that we will have less information compared to the general picture at the intersection. Also, you have problems associated with maintenance cost and what have you. Then another thing is that, to the best of our knowledge, we have not seen any commercial implementation that incorporates the advantages of V2X implementation, which we will see in a moment. Now, another problem is the traffic preemption of the presentation. Now, the V2X communication that is facilitating the implementation of our approach, we considered four different messaging formats, which is the signal request message, and then the intersection collision avoidance message, and then we have the signal timing and signal phase and timing message, and then we have the priority notification message. Now, the vehicles at an intersection will transmit these messages. That is the signal request and the intersection condition. And based on this information, the intersection controller will process the signal request message. The ICA is a vehicle-to-vehicle communication, that is what enables the information of how vehicles move around the intersection. So this is a vehicle-to-vehicle, and this is a vehicle-to-infrastructure message. Now, the intersection itself is what will transmit the signal phase and timing messages, as well as the priority notification. Now, the signal phasing and timing message is what is used to communicate schedule to connected vehicles. Then the priority notification message to facilitate the communication between multiple intersections. Now, how do we see an intersection in this work? Essentially, we consider an intersection as consisting of two zones. We refer to, we have the critical zone and then the intersection zone. Now, because we have said that vehicles transmit signal request messages, which is what is used by the intersection controller, that is the centralized component, to schedule what phases should utilize the intersection. So vehicles are able to do that once they are within the intersection zone. Now, going back to the proposed system design, we look at the decentralized unit. Essentially, the decentralized unit functions using the LiDAR, GPS, and waypoints. And the GPS and waypoints essentially is what we use to implement the pure pursuit algorithm, which allows the decentralized unit to track points. Then the LiDAR is used to controlled by the disparity extender, which helps the decentralized component to avoid obstacles. Now, the signal phase and timing signal is what the centralized intersection transmits to the centralized unit, which around the intersection, that is within the intersection zone, the vehicle takes that into consideration, and within the critical zone, it can also transmit and receive the intersection frequency, and that put together is what is controlling the vehicle at the intersection. Now, the centralized component, we see that we have the control algorithm, and because vehicle transmits signal request messages, these messages are collated, and so the control algorithm will determine which phases will be given the next schedule, and that the vehicles on those phases will then be taken out, and their information is fetched using 4 different parameters. And these parameters are what we will see in the fuzzy system, and these parameters will the waiting time, the speed, and the distance of the. Now, why this is important is because we look at the situation where even under very low traffic demand, a vehicle approaching may not have to necessarily wait, because once there is a transmission of SRM and it is received, the centralized controller can preempt given point and NS3, which allows for the communication that implements the V2X idea. We implement the the fuzzy logic controller using the Java Fuzzy Light API. Now, to assess the performance of our approach, we assessed it using 2 different traffic scenarios. We considered an isolated intersection, that is a single intersection of our system. So in the future, we will consider things like this. And that is it. So in the summary, we have considered a traffic control problem in this work, and we see that traffic intersections comes in different design, and that introduced some kind of delay.
Thank you. And setting up your problem and explaining the problem. I was missing a little bit in terms of discussion over the methodology and discussion of the results. That's probably what I'm going to focus my questions on for this. And I will give my notes to your supervisor that I made an thesis with that. I guess one thing that is important, but you covered it in your slides, is you should really, in your thesis, separate your contributions and objectives, and clearly state what the objectives of your work are. Right now, it's kind of all mixed together. Okay, so I guess the first question that I have, and the thing that I need clarification on, is when you say 2-way or 4-way, what does that look like in the figures you have? So you have a single intersection figure.
So let's take this for example. When I say 2-way, it simply means that you have less traffic on these approaches than you have more traffic on these approaches.
Okay.
Yes.
So what's 4-way?
4-way, you have traffic on all the 4 approaches.
So in your simulations, you are considering either 2-way
yes,
or 4-way.
Yes.
Okay. So I guess that's the next question, just in terms of setting up the simulation, so that I fully understand this. Is a lot of your messages, or when you send your messages out, you're looking at north-south, right, lane.
Yes,
and then you have your car coming in, you will either go east, west. So I guess what I'm trying to understand, or what I'm asking is, how are you, or when you're doing your classification for your centralized control for the entire intersection, are you considering the switching time or the phase time when you're moving from one to another?
Okay, so
Like, how is that happening?
yes, so what happens is the centralized when we approach the transmission messages, and of course the intersection controller acknowledges the receipt.
I understand that part, but what I'm wondering is how the centralized controller, like your system is your fuzzy controller is for your intersection centralized. It's the thing that's turning the lights on.
Yes.
On the road, right? You know, pedestrians are there, bikes are there. There are a lot of other things there. A lot of other stuff is in there, right?
Yes.
The question is this an infrastructure problem, the whole problem that you are dealing with, or it's you are trying to see that it's a problem from the laser perspective?
So it is both an infrastructure problem and the control algorithm also, because it is an infrastructure problem from the perspective of the range of dictation, like we've said, and then from the control algorithm itself, which is where we said that so most of the approaches do not have the capability to handle the immunization that is associated with traffic flows. Now, if you're looking at it from the perspective of other road users such as pedestrians, we also have a pedestrian to vehicle communication capability. So all of this, where essentially we tend to use mobile phones. So that is why I said that our assumption is connectivity. Every traffic participant should have connectivity, and in this case, we have
that people when they read the thesis understand that you are focusing on these aspects. And then I would caution to use the term control, because the external is from that area, I believe. Control can be, defined in different ways. I think the reasoning that you have in control is the traffic flow control, which is different than the control we have in the control software. You are not doing any control work here, right? So it's not, you do not have any controller.
I do have a controller, because the fuzzy inference system itself is called the controller. And then I have the algorithm that interferes with this fuzzy inference system to determine which length will be assigned the green wave.
Okay, so you have the controller models in the, I didn't know, I didn't see that.